Let's go ahead and jump into our 3-point test cross. So this can be really confusing the first time that you look at it just because it's totally new and there's a lot of steps. Just get some practice with it. It'll get easier as you kind of get in the rhythm of doing the steps. But yeah, let's go ahead and talk about it. So first, let's look at the name and figure out what it is. So 3-point means 3 genes. We're usually going to use this to try and figure out the order of genes, so knowing which one is in the middle and stuff like that. And test cross means you're crossing something with a homozygous recessive individual. Little a, little b, little b, little c, little c. And that other parent is going to be a heterozygote, and they could be in coupling or repulsion. So what does this look like? Well, if my heterozygote parent is in coupling, I know I have all my dominant at the top and my recessive at the bottom because they have to be a heterozygote, so they have to have one dominant, one recessive. And this is going to be crossed with a homozygous recessive male. And just so you know, for repulsion, that heterozygote parent could look something like this. Basically, just some combination of dominant and recessive. I'm going to make this C a lot bigger right here, so it's super obvious that it's dominant. Okay, so let's talk about a couple of things here. So first, let's look at the male. There are some species that crossing over can't happen in males, and so it's not even really something to consider. But let's say that it is something to consider. If I were to grab little a and I cross over and I grab little b, little c, did anything change? Did I get a new combination of alleles? Well, no, because I was going to have little a, little b, little c regardless. So we don't have to consider crossing over in that homozygous recessive individual. But we do have to consider it in the mom, because if she was had crossing over happen, for example, she could have big A, cross over, grab little b, grab little c. That's a new combination. The next thing that I want you to consider is that if you have two parents, we know that they each give one chromosome to their kids. So if you look at dad, he only has a little a, little b, little c chromosome to give. So that means that every single one of his offspring will have a little a, little b, little c chromosome. And with mom, she could either give the big A, big B, big C chromosome, or the little a, little b, little c chromosome to her kid, or some combination of crossing over happens. All right, so let's go through our 5 steps for solving, and we're going to dive into each one of these a little bit more. So first, determine the middle gene, then find recombination frequencies, then find the frequency of double crossovers, then calculate coefficient of coincidence, and finally, we're going to find interference. So let's do each one of these. Step 1 is determining the middle gene. So the first thing that you're going to want to do is looking at your chart, you're going to find the non-recombinants and your double recombinants. Your non-recombinants are your highest numbers, and your double recombinants, where the places that double crossovers occurred, are your lowest numbers. So keep in mind, we already know that non-recombinants is always going to be bigger than recombinants, just because crossing over doesn't happen every single time and things like that. So if we already know that one crossover results in lower numbers, having 2 crossovers results in really low numbers. So you're just looking at the chart, find your highest numbers, find your lowest numbers. And then you're going to draw the genotype of the non-recombinants next to the genotype of that double recombinant. I'm going to add that word in here, of the double recombinant. And then you're going to identify which allele does not match, which one is different than our non-recombinants. And that's going to be your middle gene. So once you decide that, just draw a chromosome with that gene in the middle. Some people like to go to the chart and redraw everything. If you need to do that like the first couple times that you do a problem, that's okay. But by the time you get to the exam, I would recommend trying to get away from that just because that takes a lot of time and you don't have a bunch of time to solve these on an exam. Let's go ahead and try step 1. So we're going to first determine the middle gene given this chart. Let's run through our steps. So step 1, we're just going to find our biggest numbers and our smallest numbers. So my biggest numbers are right here, 113 and 107, and that's my non-recombinants. And my double recombinants are going to be my smallest numbers, which if you look at the numbers would be 2 and 1. And then in step 2, I'm going to draw it out. And specifically, I'm going to put a non-recombinant and recombinant next to each other based on the number of pluses they have. So the ones with the most pluses are going to go next to each other. The ones with the least will go next to each other. So for my non-recombinants, I have two options, a plus b plus c plus with little a, little b, little c. And remember that little a, little b, little c came from dad. And another thing just to know whenever you're looking at these charts, the order that's given does not necessarily mean that's the order the actual genes are in. It's given arbitrarily. All right, and then my other option for a non-recombinant is just all the littles together. All right, so now let's do step 2 for my double recombinants. I'm just going to draw out what the chromosomes look like just right next to it. Then my other one would be ABC plus with ABC. So notice that my one that had 2 pluses, I put it with the thing that had 3 pluses just because that has the most pluses there. My one with 1 plus, I put it with the one with no pluses because that's the least amount of pluses. And that's just my personal preference whenever I'm looking at these. So then I'm going to compare and I'm going to see, okay, what's different? So I know that in my top one for my non-recombinants, I have 3 pluses together, plus, plus, plus. And I go over to my recombinant and I have plus, plus, nothing. So C, there's something wrong with C. C is the odd one out. It's not doing what the other ones are doing. It's not doing what the majority is doing. I go to my other one, I have no plus, no plus, no plus, no plus, no plus, plus. So again, C is the odd one out. And that means that C is the middle gene. And the way that we found that and that we know that to be true is because first we compared it to the non-recombinants. We said C is different, and the ones that we compared are the ones that correspond to the lowest numbers in our diagram. So it's the lowest numbers in our diagram. That means the double crossover had to happen, and C is the one that's different. That must be the middle gene. So the last thing that I'm going to do is draw what the heterozygote parent would look like. So I know that from her non-recombinant kids, they have A plus B plus C plus. So that means that she had to have all pluses on the top and all no pluses on the bottom. So she was in coupling. And I know that C is in the middle. So that means that she is something like A plus C plus B plus with A, C, B. And this is going to be helpful whenever we're talking about crossing over. So we found our middle gene, we determined what our heterozygote parent would look like, and we put it in the right order. All right. So now let's go ahead and go on to step 2. Step 2 is determining both recombination frequencies. And what I mean by that is the recombination frequency between A and C, and then finding it between C and B. So first, using the drawing that we just made together, that yellow thing, you're going to draw what a crossover between the left and middle genes would look like, and then write down what alleles would show up together. And then you're going to go to your chart and find the 2 places that those alleles are together. And then you're going to determine the recombination frequency, which is the number of recombinants divided by the total offspring. So to find the number of recombinants, you have to do, you're going to add 4 numbers together. The first 2 are the ones on the chart that you found, and the other 2 are the double crossover numbers. We have to include the double crossover numbers because in order to have a double crossover, you have to have a crossover in both spots, meaning you crossed over between that first and middle gene. So you have to include it when you're calculating the recombination frequency. And you're always going to divide by the total number of offspring. And then you're going to do the same exact steps, but for your middle and right genes. So first draw a crossover to show what the crossover between, draw a line to show what the crossover between the middle and right genes would look like, write down what alleles would be together, find the places on the chart where those alleles are together, and calculate the recombination frequency, remembering to include those numbers from the double crossover as well. So let's go ahead and try step 2. So I'm going to carry over what we learned from our last slide, which was that mom looked like this. All right, so now I'm going to figure out first, what does a crossover between A and C look like? And then what a crossover between C and B looks like. So I'm going to look at my heterozygote parent and figure out what would the kids look like. And remember, they're always going to get a sig from mom and a sig from dad. So looking at this heterozygote parent, if I'm traveling along the top right here and I have A plus, and then I cross over between A and C, and I grab little c and little b. So a plus, little c, little b. Or if I'm traveling along the bottom, little a, cross over, grab c plus b plus. And those would be my two options from law. So I can have a plus with a c and a b, or I could have little a, c plus b plus. And remember, for each of these, you're also going to have that chromosome from dad, because he's always going to give that little a, little c, little b. So I'm looking for that combination in my chart. So I'm looking for anywhere that there's an A plus with a C and a B with no pluses, or a A with no plus, C and B with pluses. So I go to my chart, and remember, it's not going to be in the same order, but it'll be the same alleles. And I try and find that, and I notice it happens right here. I have A plus, little b, little c's, or A with B plus, C plus. And these are stacked on top of each other. That won't happen every single time. So this top one shows up at 53. The bottom one shows up at 47. So now I'm going to calculate my recombination frequency between A and C. I do the two numbers I found, I add those together, and I also add the two numbers from my double crossover, because we had to have a crossover between A and C in order for a double crossover to happen. So I add together 2 and 1, and I divide by the total number of offspring, which is 461. I'm going to do that really quick. And you should get 0.223. All right, so now let's go ahead and see what would happen between C and B. So let's think about what that crossover would look like. If I'm traveling along the top, I go A plus, I go C plus, and then I cross over because I'm looking for between C and B. So A plus, C plus, cross over, grab little b, or little a, little c, cross over, grab b plus. So let's write down those options. I have either A plus, C plus, little b, or A, C, B plus. And remember, you're still gonna always have that second chromosome from dad. So now let's find these on the chart. So if you go to the chart and you're looking for that, you should find it with the 71 and 67. 71 has the A plus, the C plus, and the B. And the 67 has the A, C, B plus. So now I calculate my recombination frequency between C and B, and I'm going to add those two numbers together, plus the numbers from the double crossover, and divide by the total. So 71 plus 67 plus 2 plus 1 divided by 461. You should get 0.306. So if I were to draw just a little chain thing with A, B, and C, the recombination frequency between A and B would be 0.223, and between B and C, the recombination frequency is 0.306. All right. So we found our recombination frequencies. Now let's go ahead and go on to step 3. Step 3 is finding the frequency of a double crossover. So in order to have a double crossover, we need to cross over 2 times between the left and the middle gene and the middle and the right gene. So let's draw that really quick using our example that we're working through. If I were having a double crossover, I'd be traveling along this top one, A plus, cross over to the bottom, grab little c, and then cross over in that second spot and grab b plus, ending up with A plus, C, B plus, or A, C plus, B. So that's what a double crossover looks like, and you'll see there's 2 spots that it happens. It happens here and happens here. And what does and mean? Multiplication. So we're going to multiply the possibility of having a crossover between the left and the middle genes between A and C with the probability of having a crossover between the middle and the right genes, C and B. So basically, we're just multiplying the 2 numbers we found in step 2, because step 2 told us the probability of having a crossover between A and C and it told us the probability of having one between C and B, and a double crossover just happens with both this and this. So all we do is multiply those together. So let's find the frequency of double crossovers. We're going to do the frequency of A to B times the frequency of B to C, and A to B, oops, sorry, have this backwards. From A to C, since C is our middle gene, and then C to B. And from A to C, we found 0.223. And from C to B, we found 0.306. So then if we multiply those two together, since we want both of them to happen, the frequency of a double crossover should be 0.068. Okay, now let's go on to the next step. So step 4 is determining the coefficient of coincidence. This is a super fancy way to say what percentage of crossovers do we actually observe. And it's going to be the number of double crossovers that you observed divided by the expected number of double crossovers. So your first step here is going to be finding the observed number of double crossovers. And this terminology of having observed and expected should remind you a lot about chi-square. And it's the same kind of idea for observed, that's just given to you. It's going to be in the chart. And we know for double crossovers, it's the two smallest numbers. So for finding your observed, you're adding together those two smallest numbers in the chart. For expected, again, it's the same exact way as chi-square. You do the total number times the probability of it happening. And the probability of having a double crossover event, we just figured out in step 3. So all we're doing is doing total times the probability we found in step 3. And then we're going to do the division, observed divided by expected. Let's try it out. So first I find my observed, which is my two smallest numbers added together. 2 plus 1 equals 3. That's the number of double crossovers I observed. To find my expected, this is the total times the probability of a double crossover happening, which is 461 for my total, times 0.068. We got that 0.068 in step 3 by multiplying the two recombination frequencies together between A and C and B. And so for expected, I expected to have 31.5 offspring with a double crossover event. Obviously we had 3, so that didn't happen. So my coefficient of coincidence is just observed divided by expected, 3 divided by 31.5. And you should get 0.095, which I'm going to go ahead and round up to 0.1. So that means that I observed 10% of the double crossovers that I expected to have. So now let's go ahead and go on to interference. And interference is the probability of not observing a double crossover, so it's the opposite of that coefficient of coincidence value. And it can happen for a number of different reasons. For example, if one crossover occurs, it can interfere and make it less likely for another to occur. Just think about how much work that is to do a crossover. If they do it once, they don't really want to do it again. That's a lot of work. So having a double crossover just isn't as likely. Different things can happen to interfere. And you can think about this two ways. It's either the number of double crossovers not observed divided by the expected number, or the easier way, 1 minus the coefficient of coincidence. And that's what we're going to use. So interference is 1 minus the coefficient of coincidence. 1 minus 0.1 gives you 0.9. And that means that we are not observing 90% of the double crossovers that we would expect to observe. So that's what I have for the 3-point test cross. Make sure you practice with it. It will make more sense the more that you do. And eventually you won't need every single one of these steps because you'll be able to kind of see things as you go and recognize patterns that you'll be able to do a lot faster. So yeah, get some practice and good luck.
I hope you found this video really helpful. The concepts and information presented in these videos will be true no matter what genetics class you are taking. However, the concepts presented in this video are referencing material currently covered in Baylor University's coursework. Remember, if you are currently enrolled as a Baylor student, we offer free tutoring services. Our tutoring center is located on the first floor of the Sid Richardson building. You will find all the details you need to know about these services on our website, www.baylor.edu/tutoring. You may schedule a free 30-minute one-on-one tutoring session online through Navigate, or just drop in during our open business hours. For more information about our current services, please visit our website. Thank you.